Awesome. So we are very happy to be here, and we will try to rise to the bar that James let us go up. And it's wonderful to be here in Berlin and Nullcon, and we are very happy. Today we will speak about privilege escalation vulnerabilities that we were able to gain using by changing the colors of the RGB of the peripheral devices, the keyboard, the mice, and of course the wonderful thing, the mug holder. So without further ado, let's start. I'm Eran Shimoni, security researcher at CyberArk, mainly focusing on the discovery of and exploitation of local privilege escalation bugs. Besides that, I really like drinking and mixing cocktails and doing meditation.
Hello everyone, my name is Talos and I'm a vulnerability researcher at CyberArk Labs, focusing mainly on operating system internals, and except playing with kernels, I really enjoy and practice CrossFit.
Awesome, so let's start. What do we have on our menu today? First, we will examine with the thing we consider is vital in any kind of offensive research, which is the methodology we use towards open source and closed source. Specifically, we are looking at operating system and kernel models or drivers in Windows. After that, we will have some Linux internals 101, enough for us to understand the bugs, but not too much for you to run to the exit. Later, we will examine a key thing in any kind of privilege escalation talk, how the communication channels work from the non-privileged to the privileged, because if we can communicate, maybe we can find a bug. Later, we will see several bugs that are reflected by the way you change the colors of your keyboard. And lastly, we will wrap it up with a new mitigation added to the Linux kernel that reduces the severity of buffer overflow bugs from potential privilege escalation to a mere denial of service. So let's kick in. On the right, we have the beautiful penguin symbolizing a specific operating system. You can probably guess, it's Linux. And on the left, we have the not-so-beautiful broken window symbolizing a different operating system, but it can be also another one. And we will start with that. So when we don't have the source code, of course, we must do some kind of reverse engineering or decompiling to understand the gist of it. And this seldom requires us to have deeper understanding of low level and operating system. And as a result, it's more difficult and we have less things that we can learn from. The plus sides about it, if we manage to find bugs in such systems, that usually they pay higher bounty. For instance, Apple, Intel, Microsoft. In the past and now, they pay a hefty bug if you find vulnerability in their products. And the way we approach it is, first, we have the recon step that we try to read everything about our possible target. So it means a step we read a lot of blogs and see conference talk about a particular subject. After that, we look for code leaks. So one can argue that Windows is also almost an open source because of all the recent code leaks that you have. But when you have a code leak, it greatly improves your understanding if you do a decompile of the current version that you have and you compare it to your past code leak that you have. It saves a lot of time. After that, it's very important for us to define our target as closely as possible. As people who probably did reverse engineering in the past, you know that sometimes you begin with one function and then it develops to a dozen functions and then it develops to a few dozen functions, and that's a lot. And if you remember from the old days of Win32k-sys, the graphical driver of Windows that consists of several thousand functions, then things can get out of hand pretty fast. After that, usually we have some kind of reverse engineering, and sometimes we do and work with fuzzers, but more about that soon. On the other hand, when we examine open source, we have much and many examples that we can learn from because we have the code. And we can probably understand everything that's happening there, besides things that can be added in the compile time, but about that soon. Also, we can use static analysis tools, which help us to uncover several pitfalls. And eventually, we can compile and add debugging snippets in instrumentation and understand what executes on the machine eventually. And the way we approach it is first finding the code on GitHub, GitLab, or if you use the dark technology of SVN, please go to the next era, but some pieces of code are still there. We usually employ several static analysis tools, and they are mainly used to find memory corruption type of bugs, and also all the integer games that you usually find. If you have more time or you're more proficient, you can use something like CodeQL, a full-blown query language to track variables across multiple modules and functions and so on. And of course, we need to compile and build the program. Usually, we add some kind of debugging snippets or instrumentation that provide us with some feedback mechanism that help us when we execute to understand what's the status of the local variables and global data in there. And one of the cool things that we are in 2023 and ChatGPT is all the craze, but still most of the code nowadays is written by developers, and developers are human. And humans are a bit lazy, especially about code they are not familiar with. So often if we manage to find bug in one open source project, it can carry the way to a different one, and then another, and then another, and another, and another, which we will see soon. And of course, we can also do fuzzing. So let's touch the fuzzy question. To fuzz or not to fuzz? To those who are not familiar, fuzzing, in simple terms, is generating some kind of an input against a target function with having a feedback mechanism that tracks code coverage. Sounds nice and lovely, and it's a lot better than the brute force approach. The caveat of using a fuzzer that it takes time, and also it takes specific hardware for it to be efficient. If you used fuzzers in the past, AFL, LibFuzzer, Syscaller, whatever, you know it takes time for you to customize it to your own project. And if you only have a week or two and you don't have like crazy hardware, sometimes it's better to have something kind of in the middle, which we call a dumb fuzzer. The icon about the dumb fuzzer is here by mistake. Please don't look at it. And a dumb fuzzer, as we said, is kind of in the between the middle approach. And it's very effective in the way that if we have a specific target function or several, and we understand the input of it, like the arguments and the structures, then we can manipulate them in a smart way and do it automatically. And with that, we are able to actually find a decent amount of bugs, of low-hanging fruit bugs, and it's pretty surprising. And of course, if you deal with a large binary or with complicated system and you do not understand what the gist and things that happen there, also if you work on closed source, you probably need to use a full-blown fuzzer. It takes time, but if you have it, it's totally worth it. So if we want to sum up the open source advantages or why it's a bit easier, first we have endless examples that we can learn from and to read from. Besides that, the code and documentation and all the bugs, people are pretty generous in the open source community, we think, and it's easy to understand. There are more low-hanging fruits because people are less often looking at open source, also because vendors do not pay the same amount of bug bounty about it. Code editing is a possibility which helps us to find bugs in there. Fuzzing is a lot easier because we understand the types of the variables being used in the software. And also reverse engineering is a lot easier because we can compare the decompiled of the binary to the source code and see what was added during compile time. So with that, let's talk about the elephant in the room.
Yeah, so the elephant in the room is indeed the Linux kernel, or more specifically, the Linux kernel modules. But in order to understand what Linux kernel modules are, let's first understand the general architecture of the Linux operating system. So as you might know, most of the operating system are divided into two mainly parts, the user space and the kernel space. One of the main differences between them is that the kernel space is the actual privileged part of the operating system that can interact with the hardware. An example of interaction could be when the user requests to read a file from an external device, for example, and the request actually goes through the kernel, which eventually returns the data back to the user. When installing an operating system, you will most likely have the kernel shipped with it. So if you will install Ubuntu, for example, you will have the Linux kernel installed with it. But it doesn't mean that the kernel functionality can't be extended in runtime. Extending the kernel functionality in runtime is done via installing kernel modules, but why would you even like to do it? Most of the hardware devices, if you will want to install them, interact with them, it will require to add or to install kernel drivers, or in Linux, it will be called kernel modules. Like if you will install custom keyboard devices, mice devices, just general USB devices, most likely you will have to install a kernel module with it. So after we understood the general architecture of the operating system, let's jump back to our project. So we've conducted a research focusing on the Linux kernel because essentially each bug in the kernel is critical due to the fact that the kernel is always privileged. And one of the best places to hunt for kernel bugs is in third-party kernel modules, because again, most of the time they're less examined and they are accessible by restricted users. Exploiting kernel module bugs can have the same impact as exploiting bugs in the kernel itself. So from just a generic denial of service or to a full local privilege escalation, for example. The way we've done it is by looking for big third-party vendors and examining the code, which one of them was Razer. So as you might know, Razer is a big vendor company that focuses on gaming peripherals, and if you want to interact with them in your Linux environment, you will most likely use the Razer software. It lets you do a lot of things with the audio Razer devices. So, for example, customizing your macros on your keyboard, changing the RGB colors, changing your DPI on your mice, and even changing this lovely mug holder. Yeah, it actually exists. Razer has it. Let's have an example of what we can do with it. I tried my best to draw on the German flag. I hope you can understand it. I tried my best. So, one of the prime things that we need to understand while conducting an offensive research, as Eran mentioned, is to know how we can communicate between the non-privileged and the privileged part of our project. And in our case, it's how we can transfer and communicate between the user space and the kernel space. In Linux, there are multiple ways to do it, which we'll go briefly over the main methods with some examples that will show you how it will actually look in the open source project. All right. So first of all, the kernel module can implement the normal read and write API interfaces, which will be accessible via the normal read and write syscalls on an exposed device on the file system, for example, under /dev for character devices. It will basically look like this. Again, it will change between kernel modules, but the overall idea is the same. You have the file operation structure, which then you will need to implement the read and write APIs. And here I have an example I just written on device write, and every time that I will actually trigger a syscall write on an exposed file on the file system, my custom device write will be triggered. And as you can see, this is the definition of the write syscalls. And again, on the highlighted area, you can see that my write function will be called under the file operation structure. Another cool way to do it is by using the ioctl API interfaces. So the folks that are working mostly on Windows will know it's good. Again, on these methods, mostly each functionality will be distinguished by the command parameter, which again, most likely will be parsed on a big switch case on the kernel module implementation. Let's have a look. So again, we will need to implement our lovely file operation structure, but this time we will need to implement the ioctl API interface. And another way that a lot of people for some reason don't know, it's that the ioctl numbers are not just random numbers. They're actually, if written correctly, they're supposed to be based over multiple factors, like the expected structure that will be passed, most likely because of the size, and if your custom magic and the number of the function. And afterwards, as I said, you will most likely have a big switch case, which then will be parsed and execute the required functionality based on the command parameter. And again, it's accessible via just syscall ioctl, which we'll call VFS ioctl, which lastly we'll call our function that was implemented beneath the file operation structure. My favorite way to do it is by using the pseudo file system like procfs and sysfs, because when implementing a driver that uses this type of functionality, most likely each functionality will be exposed on a dedicated file on this file system. So if you have, like, let's say 20 functions implemented on this kernel module, most likely we'll have to interact with 20 files. And it's very good to do it because interacting with your driver, just reading and writing to files. Again, each file is a dedicated function. It's very easy and convenient way to work with your drivers from the user space perspective. And the bad thing about it, it's just to implement it. It's a bit harder, but here I have a general idea of how to do it. Let's assume that I have a driver which has my variable, and I want that the user will be able to work or to interact with it. So here I have my variable, and then I will have to implement two functions. One is the show function that will be called whenever I have a read syscall on the exposed file, and one is the store function to store a new value underneath the my variable. Afterwards, we will actually need to connect all the things together. So here you can see I have my variable, the show function that again will be triggered whenever I'm using the read syscall, the store function whenever I'm using the write syscall, and here as you can see the permission that will be on the exposed file on the file system. And lastly, as you can see here, I'm calling for syscreateFile, which will actually create the file under the sysfs file system. And here I have an example for when you're doing the read syscall. As you can see here, I'm just the normal stack trace of the read syscall, which lastly will call sysfs kf sec show. And what will it do? It will just call our show function. So again, the way to interact with this kind of driver is very convenient. It's very like working with just normal files, although it's written on the pseudo file system.
Thank you, Tal. So, although Tal said to you that sysfs and procfs is the best way, I care more about speed, and if you're in a need of speed and efficiency, you should definitely use memory map or mmap. Mmap essentially provides you a double mapping into a page that is always, if you want to use it, it must be in the size of page and more, and it provides a way for the user and the kernel to read and to write from that. And because of that, you don't need to copy any data between the user and the kernel, so it's a lot faster. And let's see a look how it's been used. First of all, we must implement a function or assign a function in the struct we've seen before, a file operation. So we can put here multiple functions. Here we assign to the mmap function the my_mmap function, which we will later use when we want to invoke mmap functionality in our kernel module. At the bottom, we can see that the my_mmap function receives two arguments, which differs from the regular syscall if you are familiar. The first one is a pointer to a device file, and the second one, VMA, is the virtual memory address that we must use. And for that, we assign a new structure that is of the type of VM operation struct, that here we have a function called .fault that will be assigned to my fault. So whenever we have a page fault on my fault, it will be triggered. This differs a bit if you are from the Windows background and you are familiar with MDL in the way of communicating between drivers, because there it's always page in and it's based on a physical page, but here it can suffer from a page fault. And the way to access it from the user mode, it's not too difficult. On the top, we can see the syscall, and on the bottom, we can see how we call it. And our last way of communicating between the user and the kernel is just netlink, which means using the socket API. And that's a really cool way because it allows us to do a multicast. So a kernel module can communicate with multiple user processes on the same time, which is very different and unique. Besides that, it supports full duplex and asynchronous communication, which is kind of neat. And the way to use it is very simple. If you ever created kind of a software that works with communication, you create a socket using netlink kernel create. Notice that the second argument, myNetlink, is of the value of 30, which differs from the TCP IP, and it's a custom protocol. And the third argument, CFG, has an assignment to the input function of a function called myReceived that we nicknamed. So whenever we send data from the user mode to the kernel, myReceived will be invoked. And the way to access it from the user mode, of course, you just create the socket. And notice again, we use myNetlink with the value of 30. And of course, they must match. So let's do a small recap of all the things we said here. We examine all of the communication ways because every time there is a copy or a write or a read operation between the non-privileged to the privileged part, it could be a potential security risk. And let's go back to our example of Razer. To see of all the kernel modules that are loaded in the memory, we just run ls mode and we look for Razer to see if it's loaded. We know that the vendor ID of Razer is 1532. It's an open source, you can read it. And to see the product ID, we run the lsusb command. Why do we need that? Because Razer supports the sysfs file system, as Tal said before. And to communicate with that, we need to have the vendor ID and the product ID. By running ls on all of that, we can see all the exposed functionality that the kernel module provides. For instance, if you want to toggle the matrix effect wave of the mug holder, we can just write echo -1 to that. And to see how it works, ooh, important colors. Okay, so let's go to the fun part of bugs. So the main type of bugs we are looking after now are memory type corruption of bugs and not heap related. So mostly null pointer dereference, arbitrary pointer dereference, any kind of bad pointer dereference, buffer overflow and buffer underflow. And they usually originate in data copying operation, memcopy, strcpy and all of that, and bad pointer dereferences. And the destination on the origin code is also called sometimes sinks, if you're familiar with this terminology. So here we have a very elaborate scheme, and on the left we have the lovely Nikola Tesla, the inventor of the light bulb, and without him we probably won't have RGB colors, so thank to you, Nikola, rest in peace. And on the right we have a sink with some RGB colors, blue and all of that. And it boils down to that we can go from the source to the sink and the sink to the source. In other words, we can have like a stick and we go both ways to the middle to verify if we have a security vulnerability. And in our case is that first we identify which method is accessible from the non-privileged user. We see what are the type of arguments and how we can control them and manipulate them in the function or in the module itself. We see if they reach and lead to data copying operation and the reference of pointers. And then we do something called backward tracing that we go back. And we do that to improve our odds of finding a bug and verifying it and having less false positive, which means, again, looking at all the copy operation to see how the data being used there can be manipulated by us. And lastly, to see if we can actually access the function. So let's see some bugs. So this is the first one we will examine. And this function is responsible to change the colors of your keyboard. The method is called Razer Chroma Extended, metric set custom frame too, and we have full control over all the arguments here. The row index, the start column, and the stop column are the keystrokes of your keyboard. The RGB data is the color that you want to change. And we also know that the report arguments buffer is in the size of 80 bytes. Can you maybe find the vulnerability here? It's not too difficult. Anyone? Okay. So the vulnerability originates in the memcopy operation. As you're probably familiar, the max size of unsigned car is 255 bytes, and row length is determined by stop column +1 minus start columns times 3. So in other words, we have 765 bytes. We know that the size of the arguments buffer is 80 bytes, so we have an overflow of 685 bytes, which is a lot. And that to itself is not enough for privilege escalation, because you also probably need an info leak if you work on a normal system, up-to-date system, but that's a very strong primitive. And if you remember, we said that one vulnerable code carries away to another vulnerable code, so this is a different kernel model, which is responsible for this mug holder. Razer Chroma MISC one row set custom frame, which suffers completely from the same vulnerability. So the mug holder that's striked in the first act returns here, and it can have tea in it, it can have beer in it, but it's most probably vulnerable to code, which is a shame. So use regular mug holders, they're also nicer to the touch. And another example, this function is responsible to change the RGB colors of your mice, and again, same error, and we found it in additional kernel modules, so on and so on. The cycle repeats. So let's finish it up.
All right, so for exploiting this kind of vulnerability, we have in Linux multiple ways to do it, and there's plenty of information on the web to exploit normal stack overflows in the kernel. I wanted to choose the modprobe path overriding technique, and I will explain it a bit. So in Linux, when you're trying to execute a new program via the execve syscall, for example, first of all, the kernel will need to know which type of binary it is or script, that it will know how to map it correctly in memory. If we follow the call stack for this exact behavior, yay open source, we will eventually get to this search binary handler function. Its purpose is exactly to check what type of format our binary is. For example, if just a normal binary in L format or a script format. And if it will fail to check the format, we will call request module, which will eventually call the call modprobe function. The call modprobe function eventually spawns a new user space process in a high privileges with this modprobe path parameter. And this modprobe path parameter is just a normal string that points into a specific path on the file system. So again, after we got the privilege of writing into kernel memory, we can just write a custom ROP chain with a specific ROP gadgets to overwrite this string to our custom malicious payload, which then, if we will trigger a bad binary, it will be triggered in high privileges. So again, what will I do to exploit it? I'm creating a malicious payload with just a bad crafted binary, and which for me, it will create a new user in the root permissions, because again, my payload will be run as high privileges, and then I will actually trigger it by running the malformatted binary, and then hopefully I will get the root. And again, my payload will just create a new user with root permissions. So as you can see here, I have a very low privileged user. I indeed have the Razer kernel modules loaded into my system. As you can see, the Razer accessory kernel module for this lovely Mac holder. I indeed can see that my Razer peripheral is connected to my machine. And now I'm running the exploit that again will change this very specific string. Now you can see that the user isn't created yet. I'm triggering the vulnerability now by just running a binary malformatted, just hex FFFF. Now I have a new user with the permissions of root. And again, there's plenty of information regarding the exploitation technique. There's a very nice blog post by Midas that explains very well. So recommend it. All right. So during the exploit development, we've encountered a newly added feature in the Linux kernel, which was a part of the Fortify Source mitigation. Essentially, Fortify Source aimed to detect buffer overflows in compilation time and to mitigate them in runtime. An example of runtime mitigation will be when you have a memcopy operation, for example, with a dynamic size. Fortify Source originally came from glibc, and got introduced into the Linux kernel in multiple steps, which introduced two modes of operation, which we'll call them mode 0 and mode 1. Mode 0 of Fortify Source aims to detect buffer overflow over an entire struct, while mode 1 aims to detect buffer overflows over a specific member in this struct. Let's have an example. Let's assume here that we have this object struct that has 3 inner members. The first is arg1 in the size of 2 bytes, the second one is an array or in the size of 6 bytes, and the last one is arg2 in the size of 4 bytes, followed by a memcopy operation on the R buffer. If we operate under Fortify Source in mode 0, we can indeed still overflow the R buffer, thus overflowing, corrupting, doing whatever we want with the arg2. But if we operate with Fortify Source under mode 1, again in the compile time of the kernel module, we cannot overflow our R buffer, so we have a much safer memcopy operation. Again, this feature, this mitigation it was very known in glibc, but it got fully introduced to the Linux kernel very recently. So we will brief very quick about its history. So first of all, Fortify Source in the Linux kernel got introduced in kernel version 4.13 in 2017, when mod 0 was turned on for both strcopy and memcopy family function. So if you have this machine if this feature is configured on your kernel and you will install a custom kernel module, you will have the protection against the overflowing the overall struct, but not specific members of the struct. Later on kernel version 5.11 or 2020, mod 1 was turned on for strcopy family of function, but mod 0 was still turned on for the memcopy family of function. Later on kernel version 5.18, mod 1 was turned on for strcopy family of function and for memcopy, but for memcopy, it was only for the compile time mitigation. So again, you could potentially overflow specific members of a struct if you have a bad written memcopy operation. And very recently on kernel version 6.1, mod 1 was finally turned on with runtime mitigation for the memcopy family of function. So what can we say about it? If you have a Linux machine with kernel version 6.1 or greater, and obviously you will have this Fortify Source mitigation turned on in your kernel, it's config Fortify Source. And if you will compile your custom kernel module in it, you will have the whole mitigation compiled with it. But most likely you won't have this feature turned on by default, and so you have to check it out if you're writing your custom kernel modules. And from my experience, if you're installing third-party kernel modules, they won't be installed with it. So again, exploiting memcopy operation on it won't be hard to achieve privilege escalation. So here, as I mentioned earlier, this mitigation is being inserted into your binary in the compilation time. And here I have the decompile code. And as you can see here, that's my bad memcopy operation. And as you can see, there's no any validation on the size being used under the memcopy operation. So again, buffer overflow, very easy. But if we compile it with Fortify Source enabled, again, compile it on a machine with Fortify Source enabled, we can indeed see that there's a check being added before our bad memcopy operation. And it's indeed checking our custom row length size, that it checks if it will overflow our custom buffer. So here it checks if it's bigger than hexa 4D. And if indeed it detects that our buffer will be overflowed, we will call Fortify panic, which essentially will crush our driver much safer. After finding these vulnerabilities, we reported them to the main repository. Again, it's called Open Razer, with a fixing PR, which was merged and released on the very same day. This repository is being used by a lot, like I think maybe more than 100,000 users. So the main developer was very rushed to send it and to send a new fixed version of his product. Multiple CVEs were being assigned to the vulnerabilities, and we have a couple of more under disclosures, so stay tuned. And there's a blog post on CyberArk Lab's site that goes much more deeply into the vulnerabilities and into the Fortify Source mitigation. And what's next? So first of all, our colleague here will show you some very neat things that we've done on Razer, but on a different operating system. So you should check it out. And we talked a lot about Linux. We've mentioned maybe Windows. So maybe next time we will mention a more Apple-ish operating system. Thank you very much.
You said that you used dropgen for the execution. Mm-hmm. What did you do with the stack cookie?
So by default, this repository was not compiled with stack canaries, and for the sake of simplicity, I disabled the KSLR on the machine.
Okay.
Yeah. And again, there's plenty of repositories for some reason that are not being compiled with canaries. I have no idea why.
Oh, really?
Yeah. Yeah. And again, we mentioned that, of course, for achieving privilege escalation, you will have to have information leak. But again, for the sake of I disabled KSLR. Any more questions?
Any questions? Thank you.
Thank you.
Thank you very much.